Okay, so in this video we're going to look at how to solve polynomial inequalities by graphing them. So it sounds kind of intimidating, but just by the name of it, but it's actually not that bad. So basically what an inequality is that it's going to be something with like an unknown is equal to, less than, greater than or equal to, or less than or equal to either 0 or another side with variables or something. And basically the objective is that we have to find out every possible value of x where in that domain it will satisfy the inequality. So for example, in the top one, in the top left, what values of x will I be able to sub into this and to ensure that it will either be equal to 0 or bigger than 0? So in order to do that, usually the first step by graphically solving it would be to sub in, to figure out what it is in factored form. So this one's already factored form, and why do you think the reason that we would want it in factored form? Well, it would be because we want the roots. Because the roots, we can easily graph it, and if it, let me show you by example now. So like x equals 3, that is one of our roots. Right there, x equals 3. And then we've got another root. If we were to isolate for x on this one, that would be negative half, and you can do that by equaling it to 0. So this is where the other root would be, and we know that this one, since it's order 2, will bounce back, and the other one, since it's order 1, it will pass right through it. So another thing that you can notice is that this was a third degree function. So because we know that because one of them is order 2, the other one's order 1, so the total number of exponents would be to the power of 3 in standard form. So we know that if it's positive and it's going to be in the if it's positive in order 3, it will be starting in quadrant 3 and it will be ending in quadrant 1. And we also know that it's going to bounce back on the first one at negative half, but then it's going to pass through the second one like this. Okay, so approximately, very approximately, that's what the function will look like. So this is saying what values of x is this going to be equal to or greater than 0? So just by looking at it, we know that it's going to be equal to 0 right here and right here, and it's going to be greater than 0 right here. So right here, so therefore, to satisfy this polynomial inequality, x must be equal to negative half right there, because we know that it's equal to it there, and then this one, it's equal to it here, and it's also greater than it past that point. So you can just write that as x when it is either equal to or greater than 3. And if you wanted to check your work, you could actually sub in different values of x. So this one would have to be negative half to see if that would be equal to 0 or greater than 0. And then this one would have to be either 3 or anything greater than 3, like 5. And if you sub that into the original inequality, if it's true, then you know that you've done it correctly. So let's take a look at another one. This one, we've got one root at x is negative 1, yes. And then the other one would be at just half, right there. So those are the two roots, and this is a degree 4 function, and it's positive, so it'll start in quadrant 2 and end in quadrant 1. And we know that both of these roots bounce back. So this one will look something like this. Very approximately. It doesn't need to be super accurate because we're not really solving for the graph, we're solving for the inequality. So when is this greater than 0? Well, in the last one we circled the roots because they were equal to, but this one I don't want when it's equal to 0, I want only when it's greater than 0. So it can't be touching the x-axis because then it's equal to 0. So we've got one right here, just this part. We've got this part right here, and we've got 3 different parts. So, therefore, and now all you're doing is just writing what these domains are. So, the first one would be when x is less than, and then this right here would be -1. And again, it can't be equal to -1, because if it was equal to, it wouldn't satisfy the equation, because then it would equal 0. But I only want when it's greater than 0, so it has to be less than. Or when x is greater than -1 and less than half. That would be the other one. Or lastly, when x is greater than half. So that would be the solutions that solve this one. So one thing that you can notice is that it's much easier to do all of these in factored form. So what would I do if I have one that's not, per se, like this one? So x to the power of 4 minus 3x cubed minus 7x squared plus 15x plus 18 is greater than or equal to 0. Well, the other two, we could easily just look at it, get the roots, graph those roots, and then plot them, and then plot like a rough little sketch of the graph, and then solve it from there. But for this one, it looks like we actually have to factor this, which doesn't look like it's going to be very fun. Except that's kind of what you got to do if you want to solve it graphically. So let's start. Hold on, my brush size is massive right now. There we go. So the first thing that you can tell is that since this is a coefficient of 1 and this is the constant, it's going to be a factor of the constant, one of the roots. So 18, the different factors of this would be positive -1, plus or minus 2, plus or minus 6, plus or minus 9, and plus or minus 18, of course. So let's try different things and see if it equals 0. So f of 1, let's do that one first. You know that 1 to the power of 4 minus 3, 1 to the power of 3 is just going to be 1, minus 7 times 1 plus 15 times 1 is 15, plus 18. So f of 1 will equal, this is going to be 1 minus 3 minus 7, simplify that to -10, plus 15 plus 18. So just even looking at that, that's definitely not going to be equal to 0. It's going to be greater than 0. If I add 15 and 18 to that, definitely not. So this one's not a factor. Let's try another one. Let's do f of -1. So now I'm going to replace all of these with negative ones. Minus 3, -1 cubed, minus 7, -1 squared, plus 15 times -1, plus 18. Okay, so let's do this. I'm just going to use a calculator for this. Let's do -1 to the power of 4, minus 3, in brackets, -1 to the power of 3, and then minus 7, -1 squared, plus 15, -1, plus 18 finally. So this one is equal to 0. Okay, well if this one's equal to 0, that means that I know that -1 is one of the roots. So in factored form, we know that this x plus 1, this will be divisible by the function. So now to get the other ones, I'm going to have to divide x plus 1 into that. So that's going to be x plus 1, and then this entire thing. So x to the power of 4 minus 3x cubed minus 7x squared plus 15x plus 18. Okay, so now I'm going to divide this one. So this x goes into x cubed this many times. So then minus, and then this will be x4 plus x cubed. This will be 0, and then minus, this will be minus 4x cubed, minus 7x squared, bring it down. So you actually have to do this for the entire thing. So I'm going to skip ahead and I'll show you what I did, and then you'll get the quotient, and then we'll work from there, because then this video will be way too long. So now if you've done that correctly, you'll get x cubed minus 4x squared minus 3x plus 18. So well, you could divide x plus 1 into that again and get another, you could get another, another quotient, except then you wouldn't be getting every single factor. So what we want to do is actually find another factor of this. We're going to basically start the entire process of factoring this all over again. So we know that this is a coefficient of 1, and it's going to be a factor of 18, and I've already written the factors all the way up here. So now this time, instead of trying 1 and negative 1, I'm going to be trying positive 2 and negative 2. And really, you could start with anything. It's just that I'm going from left to right. So, I mean, really, as long as you get a factor that works, then you could, I guess, do it any way that you wanted to. So let's try f of negative 2. And I'm skipping to f of negative 2 because I know this one's going to be a factor. So if I were to sub this in, negative 2 cubed minus 4 negative 2 squared minus 3 negative 2 plus 18, f of negative 2 will be equal to 2 times 2 times 2 is going to be negative 8, because it's negative, and to the power of 3. This will be positive, or negative 2 to the power of 2 is going to be positive 4. Positive 4 times negative 4 is minus 16. And then this is going to be plus 6. This is going to be plus 18. So, negative 8 minus 16 plus 6 plus 18. If you do the math for this, this is going to be equal to 0. So therefore, x plus 2 is also going to be a factor. So now I've got x plus 2. And let me just write this in a different color again. I've got x plus 2. And this time I'm dividing it into x cubed minus 4x squared minus 3x plus 18. Now, well, let's do this one. X goes into x cubed how many times? X squared amount of times. X squared. So then this will be minus, in brackets, x cubed. This will be plus 2x squared. Subtract these, and I will get, these will equal 0, and then minus, this will be minus 6x cubed minus 3x. This x goes into negative 6x squared minus 6x times. So this will be minus negative 6x squared minus 12x. These ones will equal 0. And then if I add these, this will be 9x, then plus 18. And then this will be positive 9. So then I can do minus 9x. And then this will be plus 18. So then I know that this is correct because my remainder is 0. Now I've got x squared minus 6x plus 9. So what are two things? One that adds to negative 6 and multiplies to 9. You can probably already tell that this is a perfect square. And that's negative 3 and negative 3, because that will multiply to positive 9 and add to negative 6. So it'll be x minus 3 times x minus 3, or x minus 3 squared. So now that we've done everything that we can to find the roots, this is a root, x plus 2 is a root, and x plus 1 is a root. And just to double check, I know that this one, x minus 3 is order 2. This one, the other two are order 1. So then it will add up to degree 4. And we know that the original function is degree 4, and it can only have up to 4 roots. So we know that we have every root now. We've got, so let's plot all of these. We've got x is positive 1 right there. We've got x minus 3, so that'll be 3. And that's going to be the one that bounces back. We've got an x plus 2, so x minus 2, one right there. And it's going to start here in quadrant 2 and end in quadrant 1 because it's a positive and it is degree 4 because it's even. So this one says that it passes through. This one says it passes through, and this one bounces back. So it's going to look like this. approximately, of course. And we're trying to figure out when this thing is equal to or greater than 0. So we've got this part right here. We've got this part right here. And actually, no. We have that entire end part, because this is always going to be equal to or greater than 0. If it was only greater than 0, then we'd have to take just that part and then this part as well. But since it's equal to, we can include the roots. So for this one, therefore, to satisfy that polynomial inequality, x must be less than -2, or x must be greater than +1. So if you want to test out different things, then that will satisfy the equation to make sure that that's either equal to or it's going to be greater than.